right, since it's time, picking up where we left off last class, we're talking about derivatives. And I thought for a second, we'd start with an example problem. I'm going to give you all a couple seconds to work this out, see if you can find out what the derivative is on your own. But then we're going to come back to it as a class. So if anybody needs a refresher, the way to find the derivative is to calculate the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So in our case, the function is going to be 2 over x. So what do we think? Anybody got it? Or need a couple more seconds to work on it? These aren't quick and easy, are they? They do take some time. That said, as a hint to check whether or not you're right, the answer is going to come out to be -2 over x squared. Yes, I cheated. I know a trick. We're going to talk about that today. All right, so to work through this problem, the first thing we're going to do, we're going to want to rewrite everything as a function, right? Like we're going to want to use our function notation. So we have an idea of what we're doing. Agreed? So we can rewrite our function as a function of t or as a function of x. We're just naming the variable, so that doesn't really matter here. And we want to write it in that derivative form. And then we want to go through, we want to replace our function notation with the actual equation itself. That's what we're doing here. And then we're going to try to rewrite everything, right? Notice here we have a denominator of t plus delta t, and here is a denominator of t. So we're going to need to get rid of that t somehow, right? And we're going to need to get rid of that delta t, or I mean that t plus delta t. Get them in terms of the same denominator. So once we do that, we're going to end up with this third line here. This 2t minus 2t minus 2 delta t divided by t times the quantity t plus delta t divided by delta t. That's a lot to say. And right away, we're going to see, hey, these cancel out. We're just going to be left with delta t. But then we're going to say, hey, we can rearrange some of these terms, right? fact, we can take this denominator and move it down. Agreed? When we do that, we'll get this cancellation of delta t. We're going to end up here. At this point, we can apply the limit. So as delta t goes to 0, this thing disappears, and we're just left with -2 times t squared, right? So the derivative of 2 over x is -2 over x squared, or since we wrote it in terms of t squared. Having said that, there's some things we should know. Not every function is differentiable everywhere. Whenever we have a vertical tangent, whenever we have a discontinuity, or a cusp. They call the second one a node. I think of it still as a cusp. Now let's think about why this might be for a second. When we're talking about the derivative, we're talking about the slope of the tangent line, right? So around this point, we're going to have this tangent line getting closer and closer and closer to whatever the tangent is at the point. Agreed? Well, coming at it from the left, this tangent line is going to be negative. Coming at it from the right, this tangent line is going to be positive. So they don't agree. We have a discontinuity in what that's going to look like. Does everybody agree with me? Makes sense? So another way to think of this, where are my erasers? Another way to think of this is by rewriting, in this case, the absolute value of x. The absolute value of x can be rewritten as a piecewise equation. Agreed? So if we were to take the derivative of this, at 0, we would want to look at it from the left, and we would want to look at it from the right. But check it out. This is going to have a derivative of 1. This is going to have a derivative of -1. I'll explain how I know that in a little while. So at 0, it doesn't agree. The limits don't agree, right? So because the limits don't agree, it doesn't have a derivative there. It would be discontinuous. Make sense? Kind of, sort of. We'll see more of this after a while. Having said that, something I should note on, something that is particularly important actually as far as derivatives is concerned, is that differentiability implies continuity. So if a function is continuous, it may have a derivative. May. Because notice, we don't have a derivative here, we don't have a derivative here, but these are definitely continuous functions, right? So if a function is differentiable, it has to be continuous. But the derivative of a function doesn't necessarily have to be continuous. Make sense what I mean? Yeah. Having said that, some more of those checks for y'all when you're at home making dinner or whatever. So a minute ago, I used a trick to solve that last problem. That's all we're going to be talking about today, is all the different rules of differentiability that'll let us quickly answer those questions. Having said that, before we can use them, we will prove them. Luckily, most of these proofs are pretty quick. So, first and foremost, the derivative of a constant function will always be 0. Now, if we think of it in terms of a graph, this is kind of obvious to us. And I say that because let's say we've got this function. F of x is equal to c. What's the slope of that? 0, right? 0 everywhere. Every secant line through this will have a 0 slope. The tangent line will have a slope of 0. And because the tangent line has a slope of 0, this thing has to have a 0 derivative. Make sense? Now, walking through the proof really quick, replacing our function with our function notation with what it actually represents, right? Just that constant. Doesn't matter what x value we pick, we're always going to get out c. So f of x plus delta x, that's just going to be c. And f of x, well, we already said that was c. So we end up with c minus c. So long before we ever apply the limit, we get 0 divided by delta x. Well, 0 divided by anything is 0. So it's just the limit of delta x going to 0 on the constant 0. So we get 0. That brings us to the constant rule. The derivative of a constant is always 0. So, as a couple examples, the derivative of 7, 0. If y is equal to 2, the derivative of y with respect to x, well, that's going to be 0. So forth and so on. Now, before we go on to the power rule, which is going to be the next rule we're going to talk about, we want to look at what's called the binomial expansion. The binomial expansion is just a convenient way of rewriting any simple a plus b raised to a power. Just a convenient way of writing this. Something to notice, we start off with x to the nth power, and every term after that decreases the power by 1. We start off with delta x to the 0th power, and every term after that raises it by a power. So we end up with delta x to the n at the end, and x to the n at the other end. Also, we have this polynomial term that keeps popping up, this n times n minus 1. The next would be n times n minus 1 times n minus 2. We're also going to be increasing our denominator by 1. Everybody cool with this? Okay, so using that, let's declare that our function is going to be equal to x raised to the nth power. Then when we substitute that back in and replace our functional notation with it, right? We're going to get x plus delta x raised to the n minus x raised to the n all over delta x with the limit applied, right? Well, this is going to give us this huge mess the moment we apply the binomial expansion. But right away, check something out. That x to the n here, it's going to cancel out with that first term of our binomial expansion. Excuse me. So what we're left with then is this huge ugly mess of n to the n times x to the n minus 1 times delta x, so forth and so on, right? Now all these terms have a delta x, so we can go ahead and lower the power of these delta x's by 1. Because we're canceling out the delta x's, right? That's all we're doing here. We're saying this cancels with this. When we do that, everything else is a delta x. So factor out a delta x, and all of a sudden we're here. Well, hey, the limit definition now, properties of a limit rather, allows me to apply the limit directly onto each of these, right? So now we're going to end up with n times x to the n minus 1. So what have we just found? We just discovered the simple power rule. The derivative of x to the n is going to be equal to n times x to the n minus 1. So let's use this. There's a couple quick examples. If we have a function equal to x to the third, applying the derivative, we're going to get 3x squared. Now here, we start off by rewriting 1 over x squared. It's worth remembering that any time we have something of this form, this is going to be equal to x to the negative a. And it's also going to be worth remembering that anytime we have the bth root of x, this is going to be equal to x to the 1 over b. So if we're given that our function is equal to x squared, right away we know the derivative of that's going to be 2x. So if we want to find the slope of this function at these 5 different points, we're just going to have to say, all right, what's the derivative? 2x, and plug in -2 for x. Plug in -1, plug in 0, 1, and 2. Make sense? So when we do, we get -4, -2, 0, 2, and 4. And accordingly, apply the derivative, then plug in each of those x values. Now, what if we wanted to know what the equation for this line was, this tangent line here at x equal to 1? How would we find it? What would it be? Well, the first thing we want to do is we want to find out what that point actually is, right? When x is equal to 1, what is that point? Well, our function is equal to x squared. So our function evaluated at 1 this is going to be 1. Okay. Our derivative, we already said, is going to be equal to 2x. And we know the derivative is equal to the slope of the tangent line, right? So let's go ahead and calculate that. Our derivative at 1 is equal to 2. So now we want to find the tangent line. To do that, we're going to use point slope formula. We know y minus y naught is equal to m times x minus x naught. So what's y, x naught and y naught? Well, that's going to be the point that we calculated, right? This thing tells us that x naught, y naught is equal to 1, 1. Because that's the only point our tangent line is going to touch on our function, right? So we know that point for sure. So let's go ahead and use it. Now this tells us that our m is going to be equal to 2. The derivative evaluated at 1. So plugging it all together, y minus 1 is equal to 2 times x minus 1. Y is going to be equal to 2x minus 1. And what we've just found is the equation for this tangent line here. Having said that, before we go to the next rule, we're going to want to remember this property of limits. That the limit of c times a function is equal to c times the limit of that function, right? Yep. So applying this now to find the derivative of c times f of x, we're just going to run through the process. We're going to say, hey, here I can pull out a c. But when I do that, I get to this point, right? Now I can just pull that c outside the limit. And we end up at c times what looks like the derivative of our function. That's all it is. The constant multiple of a function, if you're going to find the derivative of it, all you got to do is find the derivative of your function and then multiply it by c. So, as an example of that, let's look at this first a here. 2x to the 1/2. Why don't we all give that a shot on your own for a second? See what y'all come up with. Who thinks they've got it? Anybody? Well, what's the derivative of x squared? It's going to be 1/2 x to the negative 1/2, right? Does everybody agree with that? Yeah. So 2 times that, it's just going to give us x to the negative 1/2, right?
Can it be, would you write it as -1/x²? Or no? Is that not true?
That would not be true in this case. Here, I'll jump to the next slide actually to show the entire calculation. So applying the derivative, we're going to be able to pull out that 2 right away, right? And then we're going to say, all right, well, we want to apply then the derivative to x to the 1/2. When we do that, 1/2 minus 1 is negative 1/2, right? We're going to bring out this 1/2. That's where we're going to get this from. That's the power rule. The 2 and the 1/2 are going to cancel. We're going to end up with x to the negative 1/2 or 1 over the square root of x. Make sense? Yeah. So what we've done here is we've applied 2 different rules. The first thing we've done, we've said, all right, f of x is equal to 2 times g of x. G of x is equal to x to the 1/2. Is everybody cool with that? So when we apply the derivative, what we're going to find is that this is equal to the derivative of 2 times g of x. You pull out that 2, yeah? Then we're going to apply the power rule. Right? So applying this power rule, we've got 2 times the derivative of x to the 1/2. This is going to be equal to 2 times 1/2 times x to the 1/2 minus 1, or 2 times 1/2 x to the negative 1/2, or x to the negative 1/2. Does this make sense to everybody now? So, as a couple more examples, the derivative of y equal to negative 3x over 2. Well, that's just like saying x times negative 3 over 2, right? The power on x is 1, so we can apply the power rule here. When we do, we're going to lower that power by 1, so that'll be 0. We're going to be left with just negative 3 over 2. Make sense what I mean? So looking at it really quick. So we can rewrite our function this way, right? Not changed anything. Anything raised to the first power is just that thing, right? So now when we apply the power rule and that constant rule, now when we apply that power rule, what we're going to find is that this whole thing comes out to be -3/2 times 1 x to the 1 minus 1, or -3/2 1 times x to the 0, which is just equal to -3/2. So pro tip, it is always a good idea to go ahead and write out these powers. And if you see a radical, rewrite it as a power. This is just a great way to start the problem because it helps to elucidate some of what you might need to do. Does that make sense? Yeah. Actually, I think like 3 slides ahead says that exact same thing. All right. So let's look at B here. How would we go about solving B? Well, a good first step would be to do exactly what I just said, to expand everything out. So we start off with 5 over the quantity 2x raised to the 3rd power. Well, this is going to be equal to 5 over 2 to the 3rd power, x to the 3rd power, or 5 over 8 times 1 over x to the 3rd, which is equal to 5 over 8 times x to the -3rd. So applying our derivative, first thing we're going to be able to do is pull out that 5 over 8. Agreed? And now from here, using the power rule, we're going to get 5 over 8 times -3 x to the -4th power, or -15 over 8 x to the -4th. And all I've done here is applied the power rule. Yeah. So looking at it, they went ahead and applied the power rule here. We got the same thing. Now notice this intermediate step to rewrite. This is always going to be a good idea. Rewrite it in terms of powers. It's just convenient. It's good practice. It'll help you follow your work back should you make a mistake. And it'll also help you better see what to do moving forward. And we'll see some of why that is in a little while, because we're going to have other rules like product rules, quotient rules, and chain rules. And things can get a little hairy when we don't write things out like this. All right, so why don't y'all try B on your own? So myself personally, the first thing I would do is rewrite this radical. So when you do, in the denominator, you should get x to the 2/3 power. So what do we think? Do we have it? Looking at the entire process, we're given this function, right? When we rewrite it, we should get 1/2 times x to the negative 2/3. So how do they get that? Well, they applied two different rules. The first thing they did, actually, I guess they applied three different rules. The first thing they did was say, all right, anytime we have a radical, this is equal to x to the 1/8. 1/a, right? And anytime we have x to the b raised to the a, this thing is going to be equal to x to the b times a. And then they finally said, anytime you have 1/x to the c, this thing is going to be equal to x to the negative c. So applying all of this to our problem here, we've got 1/2 times 1/the cubed root of x squared. This thing is going to be 1/2 times 1/x squared raised to the 1/3. Which is going to give us 1/2 1/x to the 2/3, or 1/2 x to the negative 2/3. And then from there, they applied the derivative. And they rewrote it as a fraction. Everybody cool with it? All right, so moving on to the next rule. the sum and difference rule. Looks like a B, it's not. So the first thing we want to start off with is defining another function, h of x, as the sum of f of x and g of x. And then rewriting it under the limit, right? And then saying, hey, I can rearrange our numerator and group these like functions. But when I do that, notice this means I can break this whole thing up into two different fractions, right? This fraction and this fraction. And then by properties of the limit, we can distribute our limit all the way through. And all of a sudden, we find that, hey, this is the derivative of f, this is the derivative of g. And we end up at the sum rule. The derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. Is all we're saying here. Similarly, the difference. Wow, I did not realize that it's like sideways that ways. It's easier to see things like that when you're away from the board than it is when you're right at it. All right, so applying this whole thing, notice what we've got here is a polynomial, right? Now we can think of the polynomial as the sum of different smaller functions. We've got a function that's equal to x to the third. We've got a function that's equal to 4 times x. And we've got a constant function, right? So if we want to find the derivative of this thing, we just have to calculate the derivative here, here, and here, and put them all back together. And then, because we want it at a particular point, we just have to throw that x value back into our derivative. Is everybody cool with this? Yeah. So what does this all look like? Well, the derivative is going to come out to be 3x squared minus 4. And what we're going to end up with after that is to plug in, or what we're going to want to do rather, plug in that 1, right? We're going to find that 3 times 1 squared, well, that's 3 minus 4. It's going to come out to be -1. Yeah? And that would be this point right here. All right. What about this? What are we going to do here? Same thing, right? We're going to find the derivative. Then we're going to find what the derivative is at x equal to -1. Then we're going to use point slope formula, right? Agree? So doing all of this, what we're going to find is the equation for this line here. Well, they were nice enough to go ahead and tell us that the slope here is going to be 9. We've got our point, so that's our x naught, y naught, yeah. So now we just throw everything together. Hey, check it out. This is a tangent line. It goes through more than one point of our function, right? That's because the tangent line can go through multiple points on our function. The only thing we required of it is that it just touched one point. Not that it only touches one point, but that it, at a particular spot in our graph, it touches only one point, and at that one point, it has the same slope as our function. Make sense what I mean? So, jumping on to the actual work of all of this, first thing we're going to want to do, like I said, is find that derivative. Then we're going to throw in -1. We're going to use point slope formula. Having said that, let me give you all a second to work on this problem. I'm going to be right back. Remember, this is recording, so just jump to the next slide. That was a joke. All right. Who thinks they've got it? Any thoughts? So what this question is asking is what the slope is at 2001, right? So knowing that, we just need to apply the derivative and then plug in 1. Excuse me. Did anybody get 2813? So that concludes the end of this section. Again, would like y'all to check out the slides and go through these concept checks on your own at home. And let's jump on to week 5. All right, so we're skipping section 2.3. We'll come back to it after we get through all of these different rules. So I would prefer that we go through the rules and then come back to the interpretation of the derivative. And the first rule we're going to start off with in 2.4 going to be the product rule. If we have f of x times g of x, the derivative of f of x times g of x is going to be the derivative of f of x times g of x plus the derivative of g of x times f of x. And the way we get there is by starting off by representing one function as f of x times g of x, then rewriting it. And then we add in a term here. This is just adding in a 0, right? Because this effectively cancels with this. Make sense? So from there, we're going to rearrange everything. Right? We group all of our g of x terms, all of our f of x terms. And then we're going to factor things out. We're going to find that, hey, this part, it just becomes f of x plus delta x under the limit. This part, this is the derivative of g of x. That's all coming from this. Similarly here, right? So if you have the product of two functions, the derivative of that product is going to be one function times the derivative of the other, plus the exact reverse. Makes sense what I mean? So let's look at this a little bit. Again, the derivative of f of x times g of x is f of x times the derivative of g of x plus g of x times the derivative of f of x. And when we apply it, notice here, we could simplify this, right? We could expand everything out and turn it into a polynomial that's we can calculate, right? It would look something like -8 times x to the third power and blah, blah, blah. But we could do something with it. That's going to take a while. And then we're going to have to apply the derivative. So why don't we just apply the derivative straight to this? When we do that, we're going to keep that first part times the derivative of the second part plus the second part times the derivative of the first part. Now we can expand everything out. It's a little bit quicker. A little bit. Does this make sense to everyone? Cool. So as another example, we've got our first part, our second part. Well, the derivative of that first part, that's going to be -x to the negative second power, right? And the derivative of that second part, well, that's just going to be 1. So now we put it all back together. We calculate. So I personally, when faced with these problems, what I like to do is I would say, all right, so I've got f of x is equal to 1 over x plus 1, correct? Times x minus 1 I might name these. And say, all right, the derivative with respect to x of g of x is equal to negative 1 over x squared the derivative of h of x with respect to x. This is just going to be 1. The derivative of f of x is going to be equal to g of x times the derivative of h of x plus h of x times the derivative of g of x. I like to calculate these out separately and then put it all back together. And the reason why is just it's easier to see what you've done, right? Like notice going through this is an eyesore. This sucks to read, doesn't it? Like if that part wasn't purple or pink or fuchsia or whatever the hell that color is, you'd be searching for those derivatives for a little while, right? But if you break it out separately like this, it's straightforward and you can trace your work back. So this is, like I said, just me and myself, one technique that I like to use. But in the end, the work's going to come out to be the exact same. Or the result, I should say. So what's the difference between these? In this example, the only real difference is that they're both technically product of two functions, right? In the first one, you got the product of 2x times the quantity x squared plus 3x. And in the second one, it's just a constant function. Excuse me. We could apply the product rule to both of them, or we could have just applied the constant rule to that second one, right? But in either case, when we work through these, we're going to work them out the same way. Constant multiple rule, product rule. The reason why I want to point this out is because this is going to show up a lot in calculus, where you could apply a couple different rules. One's going to be quicker though than the other one. Like, yeah, okay, we could apply the product rule here, but that's going to take forever. Instead, if we recognize, hey, this is just the constant multiple rule, it's a little bit quicker. Makes sense what I mean? Cool. So far we've only talked about 2 factors, but we could have 3, we could have 4, we could have 5, we could have 6. We could have as many as we want. Now check something out. What have they done here? If we think of f of x times g of x as another function, and h of x as its own separate function, then this is the derivative of the first part, right, times h of x. And this is the derivative of h of x times our first part. So they kind of daisy chain the product rule together. Make sense what I mean? Yeah. Looking at the next rule, the quotient rule. All right, the quotient rule is the one that everyone struggles with the most. I'm going to be honest with you. And the reason why is because what you end up with is the derivative of your numerator times the derivative of your denominator minus your numerator times the derivative of your denominator divided by your denominator squared. That's a pain, right? Like just looking at it, this hurts. In a second, I'm going to show y'all an alternative way of applying the quotient rule. But for right now, the quotient rule in all of its glory. Like I said, this is going to suck to remember, isn't it? This one's long. So, nice little mnemonic. Low D high minus high D low over the square root. What's below? Because everybody loves mnemonics, right? All right, so the other way to do this. Notice if we have f of x over g of x. This is really equal to f of x times 1 over g of x. Which is really just going to be equal to f of x times g of x to the negative first power. So the quotient rule could also be simplified by saying, hey, I can break these up and apply just the product rule and just the power rule. Make sense? When we do that, notice what we get is going to be the derivative of f of x times g of x over 1, right? I mean, under 1. Agreed? So here, let me write this out. Everybody agree? And from here, we're just going to calculate the derivative of f of x. We're going to calculate the derivative of 1 over g of x and combine them all using the product rule. We're going to get the same answer this way. Does this make sense what I mean? Frankly and honestly with y'all, this is how I have always done it because I hated the quotient rule. It was something that I never was able to figure out how to memorize until somebody told me this and I was like, you bastards. Where were y'all when I took Calc 1? So, pro tip, you can also apply the product rule. So looking at this example, we can do this the long, hard way. Is it y or yeah? Okay, cool. Y is going to be equal to x minus 1 over 2x plus 3. Now let's break this up into two different parts. let's call this f of x over g of x. So f of x is equal to x minus 1, and f prime of x is going to just be 1. And g of x is going to be 2x plus 3. So g prime of x is going to just be 2. Everybody cool with this? So, using the quotient rule now, dy over dx is equal to low d high minus high d low all over low squared. So now all we have to do is plug in each of these terms. So again, one of the big things you're going to walk away from with this class is just organizing information. And I tell you that, I point out this way of organizing it because the way they do it sucks yet again. If everything's written in pencil or pen, it's going to be hard to pick out each of these individual parts. But if we actually break it out and kind of organize everything, you can be like, all right, cool. This is what we're working with. This is what we've got and what we know. This is putting everything back together. As opposed to saying, all right, I have no clue where I went wrong. Let's work backwards and forwards until we figure it out. This lets us say, is my derivatives wrong? No, they're right, okay. Is my arithmetic down here wrong? My algebra? Okay, cool, that's an easy fix. But going in the opposite direction, it just sucks. Makes sense what I mean? All right, so for the sake of brevity and time management, I'm going to skip to, no, I'm not. Okay, cool. I was going to go ahead and just skip to the next rule, but it's the next section. So looking at this problem, you just want to apply the chain rule, right? Yeah. Or we could say, hey, let's use that product method idea. Actually, let's not, because we still need to go over the chain rule, and that'll show up in a second, or in the next lecture, rather. So going about this problem, I would first say, let's break up our equation into two different functions again. F of x is equal to 2x squared minus 4x plus 3 g of x is equal to 2 minus 3x the derivative of f of x is going to be 4x minus 4 the derivative of gx is going to be -3 so dy dx is going to be equal to high d low 2x squared minus 4x plus 3 times -3 minus low d high 2 minus 3x times 4x minus 4, all divided by 2 minus 3x squared. Notice that only took 2 minutes, right? So from here, it's just going to be about factoring. I mean, not factoring, but expanding everything out. And if we can, simplifying it a little bit. So the first thing, we want to find the tangent line. So we're going to have to find the slope, which means we're going to have to finish up finding this derivative. This derivative is going to come out to be -6x squared plus 8x plus 1 all over 2 minus 3x, that quantity squared. We want to know what the derivative is when x is equal to 1. So we plug that in. We get out 3. And then we apply point slope formula. So having said that, before I let y'all go, there was a hiccup on my part when I posted the last week's worth of homework. I think it's week 4 that I just posted. I forgot to hit save when I was making all of the problems. So I posted 2. I've since corrected that. There's, I think, 22 problems. I will be adding a second assignment to this weekend. Having said that, the exam will be on WebAssign. I'll update y'all more on that. And what else do I need to let y'all know? Oh, for the homework this week, it is all of that limit stuff that we were just doing to find the derivative. So I want you all to do it by hand to actually calculate out the limit and not use what we just talked about today. And to encourage you all to do that, I am offering up extra credit to anyone who actually works these problems out by hand and submits their work into me. Cool. So you're going to get extra credit if you actually do the work and submit it to me, is what I'm saying. Having said that, I'll let y'all go.